Well, hello. Welcome to another short video segment. This particular one is going to try to describe the magnetic induction that occurs when you just turn on or off the current in a solenoid. Well, here's a diagram illustrating a pretty typical situation. We have a solenoid here with current going through it, and they show some properties of the solenoid. For example, the amount of current, the cross-sectional area of the solenoid, that's marked in blue there, the B field associated with that current, although they shouldn't need to show that in this diagram because the right-hand rule will give you that direction. And then you see the little loop of wire that's surrounding the solenoid. Now just keep in mind that that is not connected in any way physically to the solenoid, and it has a very sensitive current measuring device called a galvanometer that's in line with it. So if there's current flowing through there, we're going to know how much. So what we're going to show here is when we get current flowing through there and how big the EMF is that's generated around that gold loop. So let's get started. Alright, so I made up a few parameters here to describe the solenoid and the ring. So we've got the area marked as A, we've got the current marked with I. Now here's the key. The current is changing. It goes from 0 up to 3 amps. With a solenoid, you're never going to induce anything anywhere if you have a steady current because there's nothing changing. Induction is all about change, so that's an important part of the phrase. The copper ring has an area that is about 5 times as big as the solenoid's area. So we've got that in there. So now we're going to start with Faraday's law to describe how big the EMF is. Alright, so we'll get ourselves a little bit of room to work here. And we'll start with the statement of Faraday's law, which is that the EMF generated around some path is equal to the negative of d phi dt, where phi is what we call the magnetic flux. So maybe the first thing to look at is, well, where do we have magnetic flux? And it's easy to think, well, we have it through the entire ring, right? Because that's our path. But you can only have magnetic flux where you have a magnetic field. And that's constrained to that blue shaded area there inside the solenoid. So it turns out all of the space in between the solenoid's wires and the actual copper ring does not contribute anything to the area through which we have flux. So we will not be using that at all. Alright, so let's add a little bit more to this. The definition of flux is the field times the area through which that field acts. And what is the field here? Well, it's the field generated by the solenoid, what I call the BS equation. So if we add that in there, you can find the BS equation on your AP reference sheet if you have one. Mu naught times the turns per length times the current. And of course it's the current there that's going to be changing, and so that'll become an important part of our time derivative. And then what's the area? Well, this is the area of the solenoid. I just emphasized it's not the area of that copper ring. And so if we put that back into the Faraday's law description, and we'll say the EMF. Now I'm going to drop the negative sign here. Remember that negative sign is actually a separate part of the process. It's what's known as Lenz's law, and it tells you which way the EMF will be generated. But that's not really important for the magnitude, so we'll just leave it out for now. So we're looking for the rate of change of, and then I'm going to put all of this from above down in the expression, mu naught n I, in the area of the solenoid. And then remember, with derivatives, just like with integrals, you try to take out everything that's not really changing so it's not cluttering up your derivative. So certainly mu naught, the permeability constant, doesn't change. The parameters that describe the solenoid don't change except for the current going through it. So we'll say the rate of change of the current, di dt. Now if you take stock of what we have here, of course we have the permeability constant. We were told how many turns per meter. We have the area of our solenoid, and we can find out the rate at which our current is changing from how much it changes and the amount of time that takes. In some problems you might actually be given a function of time. Here we just had a steady rate of change, or at least it was implied that way, and so we can put in those numbers. So putting those parameters in, there they are, kind of instantly appear, and here's what I calculate by multiplying all of that. An EMF, not very big, of about 1/1000th of a volt. But that's enough to maybe see a little blip on a computer screen somewhere if you've got a sensitive galvanometer hooked up to it. And there's your magnitude. Now let's talk about direction. Well, here's this diagram again, and I've actually got an accompanying diagram that shows a little better perspective as we look down the actual core of the solenoid. I've also marked a couple other things on here. We had previously described the direction of the current through the solenoid, but because that current is increasing, that's also the direction of the change in current. Remember, if it's increasing, then the change will be in the same direction, but if it's decreasing, then the change is in the opposite direction. So shown down the core here, we look at the figure on the right. We've got an inward field marked with little X's here, and we've got current that's going counterclockwise, that's creating that field. So what does Lenz's law say? Remember, Lenz's law is really the presence of this negative sign, and what it says is when you create an EMF, that EMF is created so as to try to reverse what's creating the EMF in the first place. So let's look at this. What's creating that EMF is the increasing inward magnetic field. You can imagine over time that we'd have more and more X's that show up inside that little circular region of the solenoid. So when we generate an EMF, and that EMF will eventually make a current flow around this copper loop, well, that current is going to try to fight that increasing inward field. Well, how do we fight an increasing inward field? We actually try to create a field that is outward. So what kind of current through that ring could make an outward field? And that is what we show here with these arrows and the EMF symbol. That has to be a counterclockwise current. So that's the nature of Lenz's law, that whatever's creating the EMF in the first place is going to be, I guess, resisted by the induced EMF. So it's a little complicated, but in this case we see that the current in the ring is exactly opposite the direction of the current in the solenoid, and that's because the solenoid is trying to increase. If we do this problem again and we are turning off the solenoid's power, then we're going to generate an EMF that's in the same direction as the solenoid's current. So that's just something that takes a little bit of practice. I think I'm going to stop this here. If you see problems similar to this, then you'll have at least a starting point. We could certainly change the situation a little bit. For example, sometimes we'll take a tiny little loop of wire instead of the one that's surrounding the solenoid. We could actually put a loop of wire inside the solenoid's cavity. That changes things a little bit. We could turn on and off the current. We could vary the current in the solenoid sinusoidally. All kinds of things we can do. And one last thought I want to give you, and this will maybe lead you to another one of my video segments. I don't know if you've stopped to think about this, but we described that we would induce an EMF in the gold ring, the copper ring, because of a changing flux due to the solenoid's wires. Well, have you ever thought that maybe one little wire in a solenoid, perhaps this one right here, might have an EMF induced in it due to all the other wires in the solenoid around it. And in fact, that does happen, and that'll be the topic of another video segment known as self-induction. So I'll leave it at that.